Hello and welcome back. I would like to start discussing now how we measure, or rather how we reconstruct, the particles that are produced in these high energy collisions. And I say reconstruct because, as Lesia has explained in her lecture, most of the interesting particles that we want to study are very short-lived. This means that they decay before they reach our detector, and we have to reconstruct them indirectly from the decay products. The example that I show here, the B0 meson, this is one of the particles we study in LHCb. It decays through the weak interaction and therefore has a relatively long lifetime, 1.6 times 10 to the minus 12 seconds. But even so, it travels only about a centimeter in LHCb before it decays. And we have no detector technology that would allow us to measure this so close to the LHC beams. If you're thinking of particles that decay through the electromagnetic or the strong interaction, lifetimes would be orders of magnitude shorter, and these particles essentially wouldn't travel at all before their decay. So what we see in our detector in all these cases are the stable or long-lived decay products of the particles that we are actually interested in. And there is only a handful actually of particles that do live long enough to leave a trace in our detector. These are of course the stable particles, electrons and positrons, protons and antiprotons, and then we have muons, pions and kaons. So in order to reconstruct now the short-lived particles, we resort to relativistic kinematics. Einstein tells us that E squared equals m squared plus p squared, where I've used here natural units, setting the speed of light c to 1. So this means m squared equals e squared minus p squared, and since energy and momentum are conserved in the decay of the particle, we can replace the energy of the decaying particle by the sum of the energies of the decay products. We can replace the momentum of the decaying particle by the sum of the momenta of the decay products. So if we know the energies and the momenta of the decay products, we can calculate the mass of the decaying particle. Very simple example here. Imagine you have a particle of mass m that decays into a mu plus and a mu minus. You measure the momenta of the mu plus and the mu minus. You can then calculate the energy because you know it's a muon, you know the mass of the muon, so you can calculate the energy from the momentum, and you can calculate the mass of the decaying particle. While you should take the square root here in order to actually get the mass. Now this is shown, an example of such a measurement is shown in this plot here, where we've done exactly this in LHCb. We have looked at events with a mu plus and a mu minus, and we have calculated the invariant mass. You see in this distribution, you see two components. You see here a flat distribution. This is background from random combinations of mu plus and mu minus. You have an event in which you have a mu plus and a mu minus. They have nothing to do with each other. You can of course calculate this quantity, but it's randomly distributed, so you get a flat distribution. But on top of that background, you see here these three very clear peaks, and these are signals from short-lived particles that decay into mu plus and a mu minus. And in particular, these particles are the so-called Y resonances, Y1s, Y2s, and Y3s. Now these Y resonances were discovered a bit more than 40 years ago at Fermilab in 1977, and this was actually a very important discovery at the time because these particles were interpreted as bound states of a B quark and an anti-B quark, and this was the first direct evidence for the existence of a third family of elementary particles. You see here on the left the corresponding plot from the original publication from 1977, and you see here again on the horizontal axis the invariant mass of the muon pair. You see this clear peak here around 9 GeV, and then you see this broad shoulder here. So at the time, the resolution they had on this invariant mass was clearly not good enough yet to resolve these three particles. They just saw one peak with a shoulder here. So if these particles were discovered already in 1977, why are we still interested in these particles in LHCb 40 years later? Why do we actually bother still measuring these? Now the answer is given by Richard Feynman, who says that yesterday's sensation is today's calibration channel. So we are using these particles, and they're extremely useful to us as calibration channels. And I'm trying to explain on the next slides why that is. So the first thing you can do is you can use these particles to calibrate your momentum measurement. If you calculate this invariant mass of the mu plus mu minus pair here, the only measured quantity that enters this calculation is the momentum that you have measured of the mu plus and the mu minus, because the energy you calculate from the momentum and the mass of the muon is well known, so there is no uncertainty associated to that. So any mistake you make in your momentum resolution, in your momentum measurement, will translate into a mistake in your reconstructed mass here. So if these peaks appear at the wrong position compared to the known, well-measured masses of these resonances, you know something is wrong with your momentum measurement, and you can adjust your momentum scale to make this match. On the other hand, if the positions are, if the peaks are at the right position, you know that you have done everything correctly and you're measuring your momenta correctly. The second information you can get from these peaks is from the width of the distribution. Again, the only information, the only measurement that goes into this calculation is the measurement of the momenta. And if you have an uncertainty on the measurement of the momenta, this will translate directly into an uncertainty on the mass that you reconstruct here. If this uncertainty is large, this means the width of this peak will get wider. So from the width of this peak, you can reconstruct the momentum resolution of your detector. And clearly, if we go back to this original plot here, where you see that you can hardly you cannot distinguish the second and the third peak here, this indicates that the resolution of the experiment clearly was much worse than the resolution that we have today in LHCb. We can actually also compare this measurement from LHCb with the concurrent measurement from the Atlas experiment, and you see also in Atlas these distributions are more smeared out. You still see 3 peaks here, but the second and the third peak here you cannot really resolve from each other. So clearly in this measurement, Atlas has a worse momentum resolution than LHCb. This does not necessarily mean that Atlas is the worst experiment. This just means that for this specific measurement, LHCb is better. It has been tuned to do this measurement better, whereas in Atlas they have put more emphasis on different aspects of the measurement, and they are much better at other things than LHCb. And this is an important measure that will come back again and again in these lectures, is that you tune your experiment to the physics that you want to do. So your detector will never be able to do everything equally well. You will always have to make choices, and you have to tune your experiment and your detector to the physics that you want to pursue. Now, the same method that I've explained for the example of these epsilon resonances is still used today for today's sensation. You see here 2 of the most important measurements actually from the first run of the LHC. On the left, of course, the discovery of the Higgs boson. In this particular case, the signal for Higgs decay into 4 charged leptons in CMS here. So what is done here is, instead of calculating the invariant mass of 2 muons, you calculate the invariant mass of 4 leptons, 4 charged leptons, so electrons or muons, and you combine this and you see that there is a peak here indeed at the mass of 125 GeV, which is due to the Higgs boson. You see a second very clear peak here around the mass of 90 GeV, and this is the signal from the Z boson. And the fact that you see this decay, expected decay of the Z boson, and you see it at the right mass gives you a lot of confidence, of course, that this signal here is also correct. On the right hand side, you see a measurement by the LHCb experiment here of the invariant mass of muon pairs again, and you see here a peak just below 5.4 GeV, and this was the first observation of the decay BS 0 to mu plus mu minus, and this was decay that had been searched for almost 40 years, if I remember correctly, and the first observation of this decay by LHCb was really one of the main results in LHC run 1. So with this, we are now at the end of the second part of this lecture, and I have again a little quiz for you, and again There can be more than one correct answer, and there can also be no correct answers, and we'll give the solution, of course, when we meet next week.